This example comes out of 7.1, Characteristics of Exponential Function. In the beginning parts of this example, we're told that the radioactive element radium, Ra-225 if you're a chemistry person, has a half-life of 15 days. So what we need to do first is define what a half-life is. Radioactive elements are unusual in that they decay over time. If you have a chunk of it sitting on your desk, which I hope you don't, if you let it sit there for a certain amount of time, that chunk will actually get smaller and smaller and smaller. It decays. It doesn't disappear. It actually kind of converts into energy, and it's a long story, and you need to be a physicist to know or care about that one. But it is radioactive, which means it's somewhat dangerous, but it does decay. You could have 1 kilogram, and then 15 days later you have half of a kilogram, because its half-life is 15 days. 15 days after that you'd have a quarter of a kilogram. 15 days after that you'd have an eighth of a kilogram, etc. So we're given a bit of a graph to go with this question. So we're given a graph that looks like this, has a starting mass of 1.0, whether that means 1.0 grams, kilograms, whatever, it doesn't actually matter, it's not given in this question. But we know that after one half-life, we'll have exactly half that much. After another half-life, we'll have half of that. After another half-life, we'll have half of that. And this thing will continue to decrease or decay exponentially indefinitely. And so this graph would look like something like this. Now, a good question is, should we connect the dots or shouldn't we? Now, I already have, so the answer is yes. The reason why, if you think about it, you could have masses, any mass of radium remaining. It could be 0.9, 0.56, 0.21, whatever. It doesn't have to be a whole number or an integer or anything like that. And you could have 15 days, so one half-life, or you could have 14 days, or 16.8 days, or 1.99 half-lives. And so time is a continuous variable, mass is a continuous variable. So we have ourselves a continuous graph. So the question itself here has 3 parts to it. What is m naught or m0, meaning just what's the mass at the beginning? In this case we're given 1.0, and again no units or anything involved. You could think of that as 100%, or the beginning initial mass. What does it approach? It approaches 0. It never ever in theory touches 0, but it just keeps decaying half and half and half and half of what its previous mass was every 15 days. To write an equation for m versus t is a little tricky because it's the first time we've ever had to do this, but our mass is going to be equal to our initial amount, which is 1, times 1/2 to the power of t, where t is the number of half-lives. So let me show you what I mean by that, or why that works. If you let t be 0, you've got 0 half-lives, and you've got 1/2 to the 0, which is 1. 1 times 1 is 1. So you start off with a mass of 1. After 1 half-life, you have a mass of a half. After 2, you have a quarter. 3, you have an eighth, etc. So as long as you let t be the number of half-lives, this equation isn't actually that hard to write. The base is just a half because we were given it as a half-life. That's what we're multiplying by each time. To estimate how long this mass would decay to 1/30th, that estimate could happen in a couple of different ways. We don't yet have the algebraic skills to solve where does 1/30 equal 1/2 to the power of t. That'll involve logs, and that'll come very, very soon in Chapter 8. But what we can definitely do is just graph, and we already technically have the graph of one side of this. You could graph y1 equals 1/2 to the power of x, graph y2 equals 1/30, have some reasonable window settings. My graph above would be okay, except I would need to go a little bit past 4. And so the window settings are shown on the graph. It would draw you a horizontal line on the graph, and what you'd be looking for is the intersection. So you find that intersection, and you get that x equals approximately second trace intersect, enter, 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 and you get roughly 4.9 as your x value. Now what does 4.9 mean? That's 4.9 half-lives. So if we were actually asked something more specific than that, like how many days, we'd say, well, every half-life is 4.9, or sorry, every half-life is 15 days, so 4.9 something times 15, and I end up with time is approximately 74 days. and that's about how long this sample would take to decay to 1/30th its original mass. It makes sense even looking at the graph that it went a half, a quarter, an eighth, a 16th. By 5 half-lives it would be 1/32, 1/32nd of its original mass. So we're very, very close to that. Just under 5 half-lives, so just under 75 days is the answer to that.